Welcome to Calculus 1. In this video, we're going to talk about the basic differentiation rules. Now, with the introduction of differentiation rules, it will allow us to find the derivative without using the directly using the limit definition. So, in the next couple of recordings, we will talk about all the different types of differentiation rules, and all the proofs for these rules will be using the limiting, the definition with limits, but the proofs are in the textbook, so I'm not gonna do all that during the recording. I'm just gonna show you how to use all these rules. So the very first rule is called the constant rule. The derivative of a constant is going to equal to 0. Alright, so let's assuming c is a real number. The derivative in respect of x of a constant number c will always equal to 0. So let me show you the way I will write this out. For example, if I have a function y equal to 8, alright, the way I will write it is by saying the derivative of y in respect of x, alright, of my 8. Okay, this is the way I will write it. And when I do it, my derivative of any constant, the answer will be 0. If I have like a function f of x equal to -1, I can write it as f prime of x, okay, of my -1, so that my answer will be 0. If I'm using another variable like a t, my function h of t equal to 3, the derivative or h prime of t again will equal to 0. So sometimes I will do these problems just directly doing the derivative. Sometimes I will write a little bit more, okay, from time to time. Alright, that's constant rule. The derivative of a constant is always equal to 0. Now the power rule. Let's say n is a rational number. Then the function f of x equal to x to the n power. N is a rational number. That means it's a fraction. If my exponent is a whole number can also be written as a rational number or a fraction as well. So if I have an exponent, x to the n power is differentiable. Alright, if n is a rational number and x to the n is differentiable, the derivative of x to the n will equal to n times x to the n minus 1 power. That means I will bring the exponent to the front of my variable and then minus my exponent by 1. Alright, for the function to be differentiable at x equal to 0, n must be a number such that n minus 1 is defined on the interval that containing 0. Okay, so that's assuming my x is actually equal to a 0. Alright, so the derivative of an exponent or power rule. Alright, for this example, alright, f prime of x, the derivative of x to the 4th. So the way I'm going to write it out, alright, I'm going to bring the exponent to the front, alright, and then not my exponent, and then subtract my exponent by 1, so that'll be 4x to the 3rd. So that will be a derivative of x to the 4 power. Now this one I'm going to write a little bit more, okay. I can simply just write I can simply write y prime, but this time I'm going to say the derivative of the y in respect of x will equal to the derivative in respect of y of cube root of x, cube root of x. Cube root of x can be written as x to the 2/3 power. Okay, rational exponents. Alright, the denominator determines the roots. The denominator determines the roots. The numerator the numerator tells me, my numerator tells me my x is to that power. So this is actually a 1/3 power, excuse me. So I'm going to take a derivative in respect of x to the 1/3 power. So when I'm doing my derivative, all I got to do is bring my exponent to the front and then take my exponent and minus 1. So I will write it out for right now. 1/3 minus 1. And simplify it. That will give me 1/3 x to the 1/3 minus 1 is negative 2/3. Alright, so x is to the negative 2/3 power. If I want to simplify again, that means negative exponent, I will have to flip to the bottom. So that'll give me x to the 2/3. Alright, 1/3 is implying that the 3 is in the denominator. So since I ain't got nothing on top, there will be a 1 on top. So if I simplify it, I can rewrite it as 1/3x to the 2/3 power. Alright, so for this one, I'm going to do a little bit quicker. I'm going to just say f prime of t, the derivative of my function in respect of t. I'm going to rewrite my problem by moving this exponent, by moving t to the second power back to the top. So that would be t to the negative 2 power. So the derivative of t to the negative 2 power in respect of t, bring my exponent to the front, so that will give me a negative 2. T to the negative 2 minus 1, exponent minus 1, that will be negative 3. Alright, when we rewrite it, that will be negative 2 over, since a t has a negative exponent, that will flip it back to the other side of fraction. So that will be negative 2 over t to the 3rd power. That's a simplified answer. Okay, so the power rule, the derivative of a power tells me that to move the exponent to the front and then subtract 1. Then the exponent subtract 1. Alright, the next rule is called the constant multiple rule. What that tells us is if I have a constant in front of my function, I can always move it to the front of my derivative. Alright, so derivative of a constant times my function, okay, that will equal to that same constant times the derivative. So for example, y equal to 3 over x. So if I want to take a derivative of y in respect of x, what I can do is factor out my 3 to the front. So then I will end up with 3 times the derivative in respect of x, okay, of 1 over x, because my x is still in the denominator. And we can rewrite 1 over x as x to the negative 1 power. So I will go ahead and write that. Alright, by moving the x to the top, it will be x to the negative 1. So when I'm taking a derivative, that will be 3 times, the constant 3 still in the front. Move the negative 1 to the front, that will be 3 times negative 1, x to the exponent minus 1, that will be negative 2. Alright, simplify it. 3 times negative 1 is negative 3, so that will be negative 3 over, since my x has a negative 2 power, I will flip to the other side of the fraction. That will be negative 3 over x squared is my final answer. Alright, what happens if I have a fraction as a constant up front? I can do the same thing. I can factor out my constant. So for this problem, f prime of x, okay, that will be move the 4 over 5 up front. So I will only take a derivative of x to the 3rd in respect of x. Okay. Alright, so when I'm taking a derivative of x to the 3rd, my 4/5 still up front times Alright, move the exponent to the front of the variable and take my exponent minus 1, so that will be x squared. So 4/5 times 3, that will be 12 over 5. So my final answer got to be 12x squared over 5 then. Okay. Alright, let's look at this third one. This one is writing a little bit more complicated, but what I want you to see is there's a 1 over 4 here as a constant. So when I'm taking a derivative of my function here, I can actually factor out 1/4, and I'm only going to take the derivative in respect of x of the 1 over cube root of x squared. Alright, so let's look at this 1 over cube root of x squared. If I rewrite the cube root here, if I rewrite it, that will be 1 over x to the 2/3 power, because the denominator determines the roots. So I got a cube root, that'll be x to the 2/3 power. Alright, so moving my x to the 2/3 back out to the top, okay, that will give me my negative exponent. So the derivative, the function I'm really trying to take a derivative of can be rewritten as x to the negative 2/3 power. Okay, that will make it a lot easier to take a derivative. Alright, so using the power rule, move my negative 2/3 to the front. So my 1/4 constant still up front as well, times the negative 2/3, okay, x to the negative 2/3 minus 1, that will be negative 5/3. Alright, since x has a negative exponent, so that will come to the bottom, become x to the positive 5/3. Now I just multiply this out, my fraction, that cancels out, leave me with a 2, so that will be negative 1 over 6. So my final answer, negative 1 over 6x to the 5/3 power. Okay, so this is a little bit simplifying as well, but what this objective want you to, or what this rule want you to do is factor out the constant to the outside. Okay, makes rest of the function a little bit easier to take a derivative of. Alright, the next basic derivative rule is the sum and difference rule. The sum or difference of two differentiable functions is differentiable and is the sum or difference of their derivative. So if I got two functions being added or subtracted, when I take a derivative of them, it would just be derivative of my first function plus minus derivative of the second function. Alright, so I'm going to write a little bit more on this example. Okay, so if I want to take derivative of this function, alright, my f prime of x, I can actually split up these three terms as three separate derivatives. So that will be the derivative in respect of x to the third minus 4 times, okay, factor out the constant, minus 4 times the derivative in respect of x plus the derivative of my actual constant itself, 7. Alright, so the derivative of my first term, x to the third, that will be 3 times x squared. Okay, move the exponent to the front, subtract the exponent by 1, minus derivative of x. Alright, think about it. Derivative of x We do this quite often. If we go by the power rule, the exponent is 1, so if I move this exponent to the front, that would just be a 1. And then I minus 1 on the exponent, so that will be 1x to the 0 power. Anything to 0 power is also 1, so 1 times 1 will still be 1. So the derivative of my x will just be 1, and 1 times that negative 4 give me the negative 4. Derivative of a constant always becomes 0, so that becomes 0 term. So my answer will be 3x squared minus 4. Alright, so I want you to see, I'm using this example to see, I'm actually looking at this entire function as 3 separate functions. So I'm taking derivative of 3 separate functions here. Alright, so part B, I'm going to do part B a little bit quicker. Alright, so derivative of y, I'm going to say y prime. Okay, my constant is negative half, so that'll be negative half times, move the exponent to the front, so that'll be negative half times 4 times x to the 3rd power. Okay, exponent minus 1 plus, alright, this function, okay, move the exponent down, so that'll be 3 times 2, which is 6x to the 1st power, because exponent minus 1, minus derivative of x is just 1. 1 times negative 5 would just be negative 5. So clean this up a little bit. My y prime, negative half times 4 is negative 2. X to the 3rd plus 6x minus 5. So a lot of times I will begin to do a lot of these derivatives just by looking at them. So it's good to know the basic rules. Alright, another rule I want to look at here is the derivative of sine and cosine. Alright, the derivative of sine of x in respect of x is going to equal to cosine x. Okay. Derivative of a cosine will actually equal to negative sine of x. And I can show you by the, I can actually graph the sine function to show you that every slope of the tangent line for the sine x is actually the same one as the cosine of x. That's why it's equal to cosine x. Alright, but what I like you to do is just kind of look at these two derivatives and check it with your formula sheet so you know what they are, because after a while it'll become a lot of stuff to memorize. So that's why we have a formula sheet. Alright, so sine x over 2. So this 2 in the denominator can be viewed as a constant. So my y prime will be half of the derivative in respect of x. The derivative of sine x in respect of x. And we know derivative of sine x will equal to cosine x. So my derivative will just simply be half times cosine x. Or I can put the cosine x on the numerator too, say cosine x over 2. Alright, this is sum of two functions. So if I want to take a derivative of the 2x, that would just simply be a 2. Derivative of cosine of x, if I look up, will equal to negative sine x. So that would just be 2 minus sine x is my answer. Alright. Alright, before I do the rate of change, I want to look at one more rule here. The derivative of e to the x in respect of x. This is one where we can take a derivative of a function that will still equal to itself. Alright, so if I have a function f of x equal to 4 times e to the x, the derivative of my function here will still be itself. So that will be 4 times e to the x. Because technically I can factor out the 4 as a constant. So derivative of e to the x is still going to be e to the x. Alright, this is the sum of two functions. So if I want to take a derivative of x to the 3rd, my f prime of x, my derivative of my function f, that will be 3x squared, and derivative of e to the x will still be e to the x. So this will be my answer. All right, let's take a look at this, something called the rate of change. All right, the average velocity. If you think about average velocity, like going 80 miles per hour, okay? 80 miles per hour is your rate, is your speed. And if you go 80 miles per hour, that means you're constantly driving 80 miles per hour. Okay, that's called the average velocity. So when you travel from one place to another place, okay, you can say, oh, I'm driving 70 miles per hour. That means the average velocity during that time is 70 miles per hour. That does not mean every distance you drive is the same speed, because sometimes we change speed as we drive. All right. So the average velocity or average rate of change of an object moving in a straight line is basically calculated by the changing in distance over changing in time. I'm going to denote it as delta S over delta T. Alright, so we can say from this point to that point, okay, is 50 miles. And then go from here to here, it took you, let's say, 5 hours. So that means your average speed was only 10 miles per hour. Okay. All right. Now the instantaneous velocity is a little bit different. In the instantaneous velocity of an object at any given time, I will use the notation v sub t, which is actually the limit of the changing in distance over changing in time as the delta t approaching to zeros. Okay, it's a limit of so basically the instantaneous velocity is your limit of average velocity. And also sometimes we call this the position function. Alright, well, excuse me, the top part here is called a position function. If you take the position divided by the changing time, okay, that gives you the average rate of change or average velocity. If I'm taking a limit of my average velocity, which is the same thing as saying I'm taking a derivative as well of my average velocity, okay, then I get something called the instantaneous velocity. So for example, all right, let's say f of t, my function here is 2t squared minus 3. I want to find the average rate of change over this interval 1 to 1.1. So that means on the x-axis, okay, right here, let's say is 1, x equal to 1, or time equal to 1. Over here is 1.1 seconds, using second for example. What's my average speed? Well, I got my time, but I also need to know my y value from here to here. So to find the average rate of change, what I want to do is actually substitute, okay, my time, okay, figure out the y value at this time, figure out the y value for the other time. If you subtract the two, that will give me the changing in distance, because we already know the changing time was 1.1 minus 1. So we will substitute my time into the function, and then over the changing in time, which is 1.1 minus 1. And 1.1 minus 1 is 0.1 second difference. That's my changing time. If I plug in 1.1 into this function, I believe I will get negative 0.58 minus, if I substitute 1 into this function, I will end up with a negative 1. So negative 0.58, subtract a negative 1, then divide it by 0.1, that will be 4.2. All right, so my average velocity from this time to that time is 4.2. But the instantaneous rate of change at the endpoint is a little bit different. What's my instantaneous speed at the time 1? Or we can say 1 second. All right, so the instantaneous rate of change is the derivative of my average speed. Okay. So if I take a derivative of my function, which will give me 4t, and I'm going to evaluate at time 1, f prime of 1, that will tell me the instantaneous velocity at the endpoint 1 of the interval is 4. Okay, 4 times 1 is 4. Alright, if I were evaluated at the other endpoint 1.1, 4 times 1.1 will be 4.4. Okay, this is my instantaneous velocity at the time 1 and at time 1.1. And the 4.2 is my average velocity during that time, during the entire time period. Okay, that's the difference. And when we talk about something called a higher order derivative, if I would take another derivative, okay, of this function that I just took it, in other words, take a derivative of my instantaneous velocity, I actually come out with something else. Okay, we'll talk about it in a different video. Alright. So don't let these symbol kind of confuse you. Without calculus, we can only talk about the average speed. Alright. But with the concept of derivative, if I take a derivative, okay, if I take a derivative of my average speed, I get something called the instantaneous velocity, okay, or instantaneous speed. Okay, and I can take the derivative of my instantaneous velocity that will actually give me something else called the acceleration, how fast I was accelerating. We can actually find that using calculus. Alright, that will conclude this video. I just want to show you some of these simple basic differentiation rules. Next video we will talk more of these a little bit more complicated rules. Alright, thank you for